Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 6. Finite Volume Method for Ordinary Differential Equations. The finite volume method is commonly used in the numerical solution of partial differential equations, particularly in fluid dynamics and other conservation law problems. However, it can also be applied to ordinary differential equations in one dimension. Applying finite volume method to a two-point linear boundary value problem involves discretizing the domain into control volumes, converting the ordinary differential equations into an integral form, approximating the fluxes across the control volume boundaries, and solving for the values of the dependent variable yx at the grid points. This approach is particularly useful when a differential equation arises from a conservation law, where finite volume method naturally conserves quantities across the control volumes. The basis of the finite volume method is the integral conservation law. This lecture presents the application of the method to 1D problems only. However, starting with 1D problems makes the learning curve for the finite volume method smoother, and also gives one a better understanding of its underlying principles before venturing into the complexity of multidimensional partial differential equations. Consider the following two-point boundary value problem, subjected to the following mixed boundary conditions, where P, Q, R, and G may be piecewise continuous functions. The quantities P, Q, R, and G can be stepwise varying, material-dependent, i.e., layers of materials of different properties, quantities, which may depict jump discontinuities at the interfaces. The interface conditions are the continuity of the physical property y and the continuity of physical flux, where x equals xe denotes an interface point. The finite volume method is ideal for the numerical treatment of problems with jump discontinuities. The objective of the finite volume method is to find an approximate solution to yx at specified grid points by approximating the integral form of the ordinary differential equation over discrete control volumes. The steps of the finite volume method are gridding, discretizing, implementing boundary conditions, constructing a linear system, solving the linear system. We will illustrate the implementation above steps for a generalized second-order two-point linear boundary value problem arising from a conservation law. The gridding of the domain is similar to that of finite difference method. The interval is divided into m subintervals called cells, and physical nodes are placed at the endpoints of each cell. As illustrated, a control volume surrounding the node I is constructed by the midpoints of each cell. The cell size and abscisses are defined as follows. For generality, we will assume that the cell size is non-uniform. A control volume is designated as x from xi minus 1 over 2 to xi plus 1 over 2 by placing nodal points into the middle of the cells. The abscisses of boundary nodes on either side of xi are obtained with. Near the physical boundaries, x equals a and x equals b, the control volumes are created in such a way that the physical boundaries coincide with the control volume boundaries, that is, from x0 to x1 over 2 and xm minus 1 over 2 to xm. The gridding for different cases or geometries imply different operations. for a rod, or layered materials, or cylindrical or spherical systems. The governing ordinary differential equation is integrated over each control volume x from xi minus 1 over 2 to xi plus 1 over 2. The quantities p, q, r, and g are assumed to be constant in each interval, which allows stepwise variation from one cell to another. Integrating over the ith cell x from xi minus 1 over 2 to xi plus 1 over 2 yields, where the physical flux p dy over dx is continuous. The first integral is split into two parts. The fluxes from the left and right sides of the interior surface cancel each other out due to the continuity of fluxes. Then we are left with the derivatives to be evaluated at the cell midpoints. Next, the continuity of flux at the ith node is invoked, and the derivatives at cell midpoints are replaced by their central difference formula as follows. Where pi plus 1 over 2 and pi 1 over 2 denote values of px at the cell midpoints. The second term is also split into two parts as follows. The first derivatives are replaced by the central difference formulas, and qx is calculated at the cell boundaries. The third and fourth term yield. Finally, for an interiorite cell, we find collecting and simplifying similar terms we get where implementing the Dirichlet boundary condition at node I equals 0 or I equals m is straightforward. For instance, y0 equals a can be set as d0 equals 1, a0 equals 0, c0 equals a. That is, y0 can be incorporated into the linear system as if it were an unknown. In the case of the Newman or Robin boundary condition, the ordinary differential equation is integrated over a half cell as follows. We identify four integrals, labeled as term 1, term 2, term 3, and term 4. In the first term, the derivative at x1 over 2 is replaced by its central difference approximation. The derivative at the left boundary is solved from the left boundary condition. In the second term also, the derivative is replaced by the central difference approximation. Likewise, by approximating the integrals, the third and fourth terms yield. Collecting all four terms gives the following difference equation, where the coefficients denote. This procedure is extended to the right boundary node over the control volume from xm minus 1 over 2 to xm. The difference equation is obtained as follows, where the coefficients bm, dm, and cm denote. The finite volume method equations for interior nodes and those equations derived for the boundary nodes constitute a tridiagonal system of linear equations that can be expressed as the matrix equation AY equals B. Where A is a square matrix, Y is the vector of nodal values, and C is the vector denoting the right-hand side. The resulting linear algebraic equations form a tridiagonal system and can be efficiently solved by using Thomas algorithm. In the case of applying iterative methods to solve the tridiagonal system, the necessary condition for the convergence of a tridiagonal system is that the coefficient matrix must be diagonally dominant. The matrix equations resulting from finite volume method discretization are diagonally dominant. Thus, convergence-related issues should not be expected. The advantages of the finite difference method are: discretization procedure requires integration of the ordinary differential equation over a finite control volume, allowing the interface conditions of the discontinuous source terms, as well as the Newman or Robin boundary conditions to be implemented naturally. Unlike finite difference and finite element methods, the finite volume method does not require coordinate transformation to ordinary differential equations. It is suitable for both uniform and non-uniform grids. The discretized equations are conservative, i.e., mass, momentum, and energy are conserved for each cell volume. The disadvantages of the method are: order of accuracy of finite volume method is 2, and it is very difficult to achieve higher orders of accuracy. Computational cost of boundary value problems with variable coefficients increases. With this last note, we conclude this session. See you next time with another topic. Bye.